Yes. Yeah, once again, good evening and thank you for joining us. We already have our speaker on the call. His name is Familusi Adekunle. So we'll be starting just now. Before I hand over to our speaker, let me just give a brief introduction of our speaker. So, Mr. Familusi. Yeah, you can see his picture already, and you can see his video. So he's an emerging voice in marine science and theoretical ecology. So he deals a lot with uh, modeling, and is passionate about advancing our understanding of aquatic ecosystem in a changing climate. Mr. Familusi holds a bachelor in agriculture and fisheries and aquaculture at the State University, and he earned his master degree in marine environment and resources in different universities through Erasmus Model Scholarship. So just to name a few, he was at University of Bordeaux in France. He was at University of the Basque Country in Spain, and also at University of Liège in Belgium. And he trained across multiple international institutions I've already mentioned. He's currently pursuing his PhD in biological oceanography at the Institute of the man. I don't know. I don't know how to pronounce this. Pardon me for that. I'm not a French person, but at the University of Quebec in collaboration with Fisheries and Oceans Canada. And his doctoral research in his doctoral research is exploring the use of bioenergetic models to predict how climate change impacts crustacean species. And today he will be talking to us about the importance of remote sensing in marine conservation. So join me as we welcome our speaker, Mr. Adekunle Familusi, with a round of applause. If you can unmute yourself and clap, or you can just react with the clapping emoji as we start. So over to you, our speaker. Over to you, Mr. Adekunle. Yeah, you have the floor.
Hi, everyone. Thank you very much for the introduction, Paul.
What's up?
I
Okay.
oh, can you hear me now? Can you hear me properly?
Yeah, the volume was low before, yeah, but now it's okay.
Okay. Thank you very much for the invite. I really do appreciate it, and I think you've already covered most of the grounds on who I am, basically. So my name is Adekunle, as he mentioned, or you can call me Ade if that's more convenient for you. I'm currently a doctoral student at the Institut de Sciences de la Mer at the University of Quebec, à Rimouski. And as he said, I'm specializing in theoretical ecology or quantitative ecology, whichever it is that you choose to go with. So today I'll be giving a very brief talk on the use or the importance of remote sensing in marine conservation. So I would like to say that what I'll be talking about, or my talk, is not an exhaustive list of what the importance of remote sensing is. It's merely just a reflection of the limits of my knowledge, uh, or what it is I can describe within the period of time that we'll be talking about remote sensing and its importance to marine conservation. I do believe that there are there might be a number of individuals amongst us here today who better understand or who are specialists in remote sensing. So maybe if I say something and you don't totally agree with it, do not mind me. I'm not specializing in remote sensing. I'm specializing in quantitative ecology. But we do have some interplay where I have to look for information using remote sensing, and using the limited knowledge that I have, I try to make do with it. So I will share my screen and then begin the talk.
Okay.
I think I should be able to. Okay. This is the welcome page. I'm trying as much as possible to indicate a couple of things. We do know that we're talking about the importance of remote sensing in marine conservation. There are no limitations to marine conservation. You cannot say, or we should not say, there are individual species that that we have to focus on when talking about marine conservation. There are those individuals that receive more attention than others, depending on what the situation is and depending on the area that we are looking at. So a species that is not the focus here, either due to commercial or ecological reasons, would be the focus in other places, depending on the regional realities. So what is marine conservation? Or if we were to define marine conservation for a particular area, how do we define it? We could say it is the protection and preservation of an ecosystem, not an individual organism. An ecosystem and the resource of that ecosystem through planned management to prevent overexploitation or overuse and to conserve such ecosystem in such a way that future generations will be able to have or derive benefit from it. Like I said earlier, we could have focuses. So look at threatened and endangered species, and we could have actions that we want to limit during conservation. Take, for example, commercial fishing or recreational fishing, in order to make sure that specific habitats or even entire habitats, best case, are either recovering or maintained at a pace. So globally, there are international treaties. Take, for example, the World's Future Council, the IPCC, that have goals to say 30% of the ocean should be protected by the year 2030 using means such as establishing marine protected areas. But regionally also, there are goals. Take, for example, in places like the Great Barrier Reef, where there is the need to establish some sort of heat tolerance in the reef, or for whales that we need to conserve, which are on the endangered list. Or in places where there is a lot of production of nitrates, that eutrophication is currently going on. So basically, marine conservation is making sure that what we have remains for future generations and that we do not overuse what we have. So marine conservation is reliant on several things, including research. When we do research, we want to understand what the state of the marine resources or the ecosystem is. And the goal of that is both to understand, to teach others, and then to make policies that ensure that what it is we're looking at will remain for future generations. That's the policy making and the governance part. So remote sensing is a very basic terminology. It is obtaining information about an object from a distance. An example, a very common example of remote sensing is photography. So there are several ways to collect data, and there are several sensors or equipment that can be used for that. Some are ground-based, others are airborne, others are space-borne. The method that you use or the data that you use in remote sensing is dependent on the type of information you need. How detailed do you want the information you're getting to be, and how frequently should the data be? So remote sensing principles works on electromagnetic radiation. A very common source, or the most natural form, is what we get from the sun, or the electromagnetic radiation that we get from the sun. It is reflected, absorbed, or it can be re-emitted by the Earth's atmosphere in form of infrared radiations. So satellites are carriers of sensors, basically, that can measure this electromagnetic radiation, either the one from the sun that is hitting the Earth, or what the Earth is giving back or reflecting back. So with calibrated instruments, we can measure the height, the temperature, the moisture content for nearly every feature in the atmosphere, in the hydrosphere, lithosphere, or the biosphere. So why remote sensing? We do remote sensing, or we collect information remotely about the Earth because it offers the opportunity to reach a larger area within a relatively similar period of time. So we're talking about a synoptic coverage. Take, for example, you want to assess the state of the entire North Atlantic at once. The temporal frequency also needed to capture dynamic aquatic processes. So take, for example, if you're doing science and you want to know what the chlorophyll concentration of both the Gulf of Guinea, which is quite close to Nigeria, and East Africa, or an area in East Africa, is at the same time, because you believe that there is a current that links both. It's really hard to say, okay, I'm going to fly to East Africa, and then I'm going to remain on the phone with someone who is in the western part of Nigeria, and we're going to collect our samples at the same time, and we'll do that consistently for the next couple of years. It's really hard. So remote sensing offers the opportunity to do that, in that you can collect samples at the same time with the same temporal frequency to capture dynamic aquatic processes. More so, if we look at the entire ocean, it's 70% of the Earth. It's the largest. Saying you want to go to the Pacific Ocean to go collect samples, or to the center of the Pacific Ocean, which boasts of some of the farthest area from land that we have, to go collect samples from there frequently is almost impossible. Remote sensing simply scales these challenges. Now, it doesn't just apply to the oceans, it applies to land as well. You can see the image that is here. Going to the Sahara to go understand what the state of the vegetation is, or going to somewhere in Central Africa, in the Congo, or the Amazon in South America, to go understand what the vegetation cover is quite the walk. Remote sensing scales this for us. So some of the things that can be measured via remote sensing are listed here. Temperature, wind speed, current and waves, which are also called sea surface height, precipitation, cloud cover, topography, or bathymetry when it comes to the ocean. They can all be measured. But the quality of the data that we get depends on several factors, including the size of the sensors that we're using, the system of the sensor, which I'm going to explain later, the distance between our satellite, or between our sensor and the ground, and then diffraction effect. The cloud has its own diffraction effect. The atmosphere has its own diffraction effect because it also contains ions. And the type of algorithm, or the type of system you're using for image correction, because as the radiation passes through the atmosphere, it hits things before it reaches the surface. And also after it hits the surface, before it gets back to the sensor, in the case of active sensors, you need to correct for that to get the best image. So sensors can either be passive, or remote sensing systems, they can either be passive or be active. In the case of passive remote sensors, they measure the energy that is reflected or emitted by the Earth's atmosphere system, or changes in gravity from the Earth. So the radiant energy that is coming from the Earth is converted to quantities that we need, including temperature, precipitation, or moisture. Example of these sensors that do not emit their own energy or their own radiation are Landsat, OLI, the Terra Modis, the GPM, and the GRACE. For active sensors, they provide their own energy source. If we made the sun, then we will call the sun an active sensor because it provides its own energy source. So they provide their own energy source for illumination. They can measure any time of the day. They operate in the microwave portion of the electromagnetic spectrum. So it makes them capable of penetrating the atmosphere under most conditions or cloud covers. These are mostly used in meteorology for, take for example, weather forecast and the likes. Examples are laser altimeters, uh, LiDAR, radar, and scatterometer or sounders. And some of the missions that have deployed the sensors are listed down below. So when we collect this data from our sensors, when we get it back into our computers, there are several levels that this data could be at. Initially, when we get it back, it could be at either level 0 or level 1, which is the raw instrument data that may be time referenced. It's the most difficult to use. You cannot really just look at it and understand what is going on in most cases. It requires more specialist attention. For the level 2, it's been converted into geophysical quantities through a computer algorithm in a retrieval process. It's georeferenced and then calibrated. The level 3 and the level 4 are the ones that we're more familiar with, that we can use, that we can understand, and that are mostly published in papers. They're already mapped on a uniform space-time grid and they're quality controlled. Sometimes they've already been combined with models to and pass through a process called assimilation or data assimilation. And this is the easiest, this is the most interpretable for biophysical quantities. So when we get the data, it could be in what we call a net CDF format, which is a community standard for data. Relative examples of the format that I'm talking about here is when you have a picture, it could either be in JPEG or it could be in .tiff format, or it could be in any other format. I can't really remember off the top of my head. But yeah, your pictures could be in several formats. That's the type of format that I'm talking about. You can convert from one format to another. Take, for example, the net CDF. When you've done a bit of processing on it, you can get a JPEG format. Those are the images that we have or that we see. But this net CDF are multi-dimensional formats. You could work with it in R using several packages, including NCDF4, RNetCDF. And another format is the ASCII format, which is basically just a binary text format. So when you download the data from the satellite, it would be basically ones and zeros. And if you want to work with it in R or Python, you would need these packages. Sensors are deployed on different types of platforms, so to speak. Mostly just two. There's the aerial platforms and the space-based platforms. The aerial platforms are platforms such as drones, such as helicopters, such as planes. And the space-based platforms are mostly just satellites. The aerial platforms quite differ from the space-based platforms in that when you're flying a plane or a drone over a place and it's carrying a sensor, then the resolution is often much more higher because the distance between your sensor and where you're trying to observe is really small. The aerial platforms are more flexible. You could wake up sometime and decide to launch a drone. You cannot wake up sometime and decide to launch a satellite. They are less stable in that you have a period of taking off, and when you're flying, there is interactions, there is correction when you're trying to, balance your equipment. However, for the space-based platforms, it's once you've launched it, then it follows an orbit, which could be either sun synchronous or geostationary, and then you can consistently collect data over the same spot. There is no air interaction. There is there's no need to pilot the satellite. It simply follows a consistent orbit. So your data that you get is from the same place over an entire period of time. And also, you can capture a much larger area. You cannot fly a plane from here to uh, another continent over 10 years consistently every day. So it's less costly per unit area. Your satellite is just rolling in the atmosphere and it can continue to pick up data from those places without much problems. So how does remote sensing come into marine conservation? A first example is marine protected areas. These are areas that are, saved for a period of time to allow for recovery or maintenance of ecological balance. So remote sensing helps by providing large-scale data and temporarily consistent data for making decisions on managing regulation enforcement and the biophysical state of the MPA. There are several examples of this. There are several ways to go about demonstrating the applicability of remote sensing to MPAs. However, an example that I found that is quite interesting is this paper that talked about a multi-sensor platform for monitoring vehicle activity near MPAs. Now, one of the problems with MPAs is that once they're established, or for some, they're established primarily to keep human activity in those areas to the minimum, because those activities are dangerous to a particular species. You could have anchors that are destroying beds, or fishing that is killing mammals. Take, for example, whales. So what they did in this case is to find a way to deploy several sensors at the same time into a particular area to monitor the activities of vessels in that area. And if they are violating a particular period of time, how much vessels are coming in and going out, are they approved, uh, and where they are at a particular time. So remote sensing makes this quite possible. And it's a very great example. Another example is species and ecosystem biodiversity correlates in this paper, where they monitored what areas the sharks are staying in a particular period of time. And the lines that we see on here close to the Atlantic Ocean along the Iberian Peninsula indicates where the organisms move or where they go around. And that is also shown by the heat maps that we have here. Now, mind you, this is an average of their activities over a period of time. Now, with this, we could make decisions on where to make sure that we look at, or to save space for them to move around, to browse, to reproduce. That is one of the really key things that remote sensing provides. I know several other examples and importance are available in literature. Excuse me. Take, for example, monitoring sea level change. There has been several mentions of sea level rise, mangroves, monitoring the health of seagrass beds, and also pollution, oil spills, marine toxins, plastic assemblages, the status of turbidity, and the land use land cover. Take, for example, corals. There are several ways to monitor corals, but one of the most impressive ways that I found was this tool by the National Oceanographic and Atmospheric Agency of the United States, which is called the Coral Reef Watch. It's a 5-kilometer resolution tool that gives you what the state of the corals is within a 7-day maximum. You could have several other monitoring methods as well. Now, the color coding here is an indicator for alarm, so to speak. The purple ones are telling you that the sea surface temperature is exceeding what it is that the corals can take. Now, corals are dependent on a type of holobiotic relationship with their algae, in that if the temperature is too high, then the algae has to leave the corals. And if the algae is not present, then they cannot, have enough food, because they're dependent on They're dependent on the environmental temperature, while the corals are dependent on the algae. So this is a very good example of application of remote sensing for understanding or for monitoring what the state of the corals is. And this is, I believe, between the United States and between North and South America, so to speak. And also for monitoring global sea level, a very important tool for that is Topex Poseidon, which possesses an altimeter. I don't know if you can see this picture down here, but it measures the distance or the difference in the distance between the sea surface and the sensor of the satellite. And with that, you can understand what the changes in the level of the sea is, up to millimeters. And this is what we have. Now, in addition to this, it also allows us to make projections for the future, not just with the Topex Poseidon. There are several other tools with the European Space Agency that can do this. And we have an accumulation of this data for several years. Take, for example, this is from 93 to 2020. In addition to that, to monitor mangroves, there is the possibility to use either specialist tools or to use something as ubiquitous as Google Earth Engine. Now, the Google Earth Engine is really, really amazing. It's not just for mangroves, it's not just for sea surface temperature. It's for several things. It requires a bit of technical know-how, where if you can work with, take for example, the Python script to communicate with the tools, then you can even deploy your own algorithms to understand what is going on. But yes, there's a tool called Mangroves for SDGs, where you can understand or look at what the state or what the mangrove cover is and break it down to countries using the mangrove dataset comparison tool. This is also supported by the United Nations Sustainable Development Goals and the Goddard Space Flight Center. You could go out of this and work directly with Google Earth Engine using several other methods. Still talking about mangroves, these are some of the data sets or databases that you could use to observe what the state of the mangroves is. I believe this is for salt marsh. Now, the reason why we monitor what the state of either mangroves or salt marsh is because they're responsible quite to a degree for carbon sequestration. So they respire, and when they respire, they produce quite a lot of biomass, which is very mobile. And even in addition to their really mobile biomass, talking about the leaves and stuff, they're responsible for bearing quite a lot of carbon because they respire. So they're responsible for about 10 to 18% carbon burial in the ocean. And this is stored immediately or almost immediately below the ground. So collectively, both seagrass, mangroves, they're responsible for what is called the blue carbon. And for remote sensing to observe these, it's a very unique relationship. We use what is called hyperspectral data, in which there is more monitoring throughout the spectral chain in the visible region. So since the sensor waves is not just passing through the atmosphere, it's passing through the water column as well in order to observe, and the depth of in one place is going to slightly differ from the depth in another, or the bathymetry is not very uniform. There is quite a bit of correction for in order to get the best data set. So there are several algorithms that are available for deriving either the quantity of the seagrass that you have or the quantity of mangroves that you have in a particular area. So for that, some of the data sets that are available via the Landsat platforms, the Sentinel-2, but mostly in addition to these, there is need to be there to go collect samples to validate these estimations. Other things that these are important for, or that remote sensing is important for, is monitoring oil spills. So oil spills could occur due to tanker collision, due to pipelines ruptures, due to operational discharge, and due to natural disasters. An example is the Deepwater Horizon oil spill in 2010 and the Sanch tanker collision in 2018. We need to know where the location of the spill is. For that, there are simulations that are carried out ahead. So when these simulations are carried out, you need to know the wind, you need to know the current, you need to know their velocities, and then you model how the oil spill moves. And then when it eventually happens, you can, rerun that and backtrack to where the spill is happening. So this is really very important for conservation. Oil spills are very detrimental to marine organisms, with millions of organisms dying during the Deepwater Horizon oil spill. So this is really, really critical for that field. An example is this: before the spill, after the spill. Some of the sensors that were used include the SAR optical sensors, basically a camera, and then aerials. So when oil spills happen, you cannot just rely on what you're getting from satellites because the distance is just too large. So it's best when you're using aerial sensors. Example of aerial sensors that are quite important in this is listed here: the SLAR, the laser, microwave radiometry, and the likes. But most especially your camera and video, because the ice is very good. Or because the distance, you're not very far from them, then you can observe what is going on. So when we know where the spill is happening, it makes it easier for us to make decisions on how to combat it. Are we going with in-situ burning? To what extent are we going with in-situ burning? Are we going with the addition of sorbents, oil adsorption, and then recycling? Or are we going with chemical methods? And how much photooxidation is going on, or how much has broken down from the period of the spill? So remote sensing helps this, but it's also best to have uh, sensors on aerial systems. Other things that remote sensing are quite good for is the monitoring of harmful algae blooms. An example of that is the Alexandrium species. With over 30 species, they're global, they're very ubiquitous, and they produce toxins that are quite poisoning to humans, and it causes paralytic shellfish poisoning. It also is very harmful to aquaculture and fishery industries, and it disrupts the food web, because if there is no primary production, then secondary production and secondary consumption is hindered. An example of remote sensing is what was done here in this work, where they provided a way to detect harmful algae blooms by implementing an algorithm that is corrected by sampling in person to understand the extent of algal blooms offshore. And it was really, really effective. So they got satellite data and then in situ data, did match up, algorithm parameterization and validation, and then they produced the implementation of that. Another use is detection of plastic waste. So here we have our satellite data, Sentinel-1 and Sentinel-2, which they applied artificial neural networks to. And after that, after training the model, which is, well, an interface between AI and satellite oceanography, they were able to determine which areas or what types of plastic are in the environment. The plastics are the red patches somewhere in here. So all of this is possible, like I said, because we are working with electromagnetic radiation, which can either be bounced off or be produced by our sensors. However, we can go a step further using what we call hyperspectral data sets. It's within the visible region, but still it's more like having several checks within the visible region in order to have the data that we need. However, some of the challenges of remote sensing in conservation is data access. So, as you probably may have observed, there is no central database, there's no central tool for working with remote sensing. It's depending on the information you have. So, the more you practice, the more you apply, the more you look for several or better means of doing the same thing, the better you get at actually doing it. So it requires some technical know-how, tools such as CDAS, such as R, such as ArcGIS, QGIS, and Python are quite handy when it comes to uh, remote sensing. And also, when you've gotten the biophysical data that you want, you need to understand the context of that data or the plots you're looking at. You can't just make decisions because you believe this is what the temperature is based on the data you've collected without understanding what the true realities is on ground. So field knowledge and indigenous knowledge is important to best interpret and implement the information you've acquired. Also, other challenges include cloud cover. So tools such as, take for example, microwave could penetrate clouds. Other sensors cannot do that. So you need algorithms like convoluted neural networks or artificial neural networks, like one of the papers I presented did, or DINIOF, which is a cloud filling algorithm. Now, these algorithms could also have their own inherent errors. And so those are some of the challenges. Finally, remote sensing is greatly important for marine conservation. It's a very useful tool, but there is no single way of getting things done. So it's best to not do things in isolation. It's best to share data, and it's best to work in collaboration with stakeholders in order to make decisions. And also in the future, more participation is needed, both in deployment and applications, especially in the global south. Thank you very much for listening, and your questions are definitely welcome.
Can we give our speaker a round of applause? Wow, that was nice. That was awesome. Thank you so much, Mr. Adekunle, for that wonderful talk. So if you do have any question, I can't see our clapping. So use the reaction to clap, 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 clap. Let's show our gratitude to our speaker. Yeah. That looks like it. Yeah, thank you so much. So I don't know if anyone has any question. You can just raise up your hand and then you can unmute your mic, or you can put it on the chat. Yeah. I concur, Amina. Yeah, it's a very beautiful presentation. Yeah. Okay, so if you have any question, you can just unmute your mic or you put it on the chat. So just to give a summary of our talk, we could see the importance of remote sensing, like it helps in marine conservation. Yeah, and it also helps in tracking pollution. Talk of plastic pollution. I am working on plastic pollution, so I could I can see how remote sensing is being used to track plastic pollution, oil spill, and the like. So it's a great tool, and I think there are actually courses online, if I'm correct, where you can really learn how to use these tools, so you can familiarize yourself with these tools because they can always come handy. I don't even know anything about that actually, but yeah, you could familiarize yourself with it, and then you can tell that it's a very useful tool. So do we have anyone with any question? You can get the courses on Coursera and other platform. Or Adekunle, do you have Mr. Power? I will call you, please. Adekunle, do you have any platform you could suggest where people can learn about this too?
One of the key platforms that I found very useful is NASA Asset.
Like for beginners.
Oh yeah, for beginners. There are several courses on it. I will
Can you
put a
please
link.
put it yeah. Okay. Yeah. Please put the link on the chat so you can explore the platform. You can start learning. Uh, yeah, that's good. So, Mr. Power, you raised up your hand. Can you please go ahead?
All right. Good evening, everyone. Good evening
Good
to
evening.
our facilitator. You've done a wonderful job, and I really appreciate that. Yeah, my question, actually considering your conclusion too, so I will draw my question together. I want to ask that how do we validate satellite data accuracy for marine ecosystem, especially in regions with limited field observation? I think you made mention of areas like the South, and I don't know if that is in South America or the South region, but I am so particular about Nigeria. Mostly, I work with let me put it this way: I do work with should I say Google Map? I work as a site validator. And most times, even working with Google Map, there are some bits of errors when it comes to data accuracy, maybe name of the communities, stuff like that. So I'm like, okay, how do we validate satellite data accuracy, especially for marine ecosystem, especially in regions with limited field observation? Do we have to go with is there a way when we are so particular about satellite data accuracy? You know, we don't in Nigeria, there are limited all these drone whereby you don't have access to drone and all those other features. So that's my question.
That's a very good question. Um, so one thing I can think of is to do the same thing using different means and then compare the results that you have. So take for example, I want to know what the sea surface temperature is off of the Gulf of Guinea. I will get the sea surface temperature either using data from Topex Poseidon and then get the sea surface temperature from Sentinel and then compare what the sea surface temperature of the two areas are. If there is a difference, then I will know that I have to, you know, go there in person. Or even better still, I would still prefer to go there in person, take my mercury based thermometer, put it in the water, and compare what the data sets are for exactly the same period of time. So the beauty of remote sensing is since you're going to get your data anytime, especially when you're working with satellite based platforms, you're going to get your data any day and any time. Come up with a way to do your measurements first. When you've done that, do the measurements, then go to the field, take your measurements, come back, and compare both. If there is a way to do the same thing in different ways, do that and compare all three. But that is what I would say. When it comes to more general field of marine conservation, I don't think there is a method in GIS to measure an ecosystem using just a single uh, index or parameter. You could measure biodiversity, which mostly is going to be based on something related to primary production. So since you cannot measure entire ecosystems using a single value, all the values you're going to measure, primary production, secondary production, do that in different ways, then go to the field and compare what the performances or what the differences are. I hope I've been able to answer your question.
Oh yes, thank you. I've been able to get that. It's more of a practical way than maybe any other platform or any other way to retrieve the data. So I got that. Thank you.
My pleasure.
Yep. And that's it here. Because just to corroborate what Adekunle said, that even in modeling, to validate your model, you still sometimes you still have to get the data from the lab or from the field. Yeah, there are some data you get from literature. Even the ones you get from literature, it was because of people who have done the lab work or the field work before. So to really validate your data, you really have to go into the field or into the lab to collect some data and to compare. Like, okay, am I on the right course or am I really missing the track already? So yeah, it's good to really do the practical work to be able to validate the data you are getting. So thank you so much, Mr. Adekunle. Do we have any other person with any other questions? Do we have anyone with any questions before we call it a day? Any question? All right. Okay, in the absence of no other question, well, we really, really, really want to appreciate our speaker, Mr. Familusi Adekunle. So I call him Ade. So thank you, thank you. Yeah, let's give him a round of applause. Uh oh yeah, Amina, do you have a question?
Yes, sir.
Oh,
I
okay.
think I have a question.
Okay.
Good evening, everyone. So first off, I would like to appreciate our speaker. He has really done a great job. Honestly, I enjoyed this presentation from the beginning to the end. So my question is basically on the challenges of this remote sensing. So yeah, my question is that how does because it made mention of some factors that could affect the data. But then I'm trying to picture because I really do not know anything about this thing, only if I have to go and read furthermore on it. So how does atmospheric condition affect remote sensing data? Can I get a little bit explanation on that?
So I hope I mentioned that one of the major things that affects the quality of the data is cloud cover. So on the electromagnetic radio or on the electromagnetic spectrum, there are, should I say, photons? I'm not sure if I'm using the right term, that could pass through the cloud when you're, to the heavier side of the radiation spectrum. There are others that cannot. For sensors that are based on radiations that could pass through the cloud, they do not have a problem with cloud cover. For those that are not, I think there's a particular wavelength, I don't know the exact number, that cannot pass through the cloud. So those interfere with the ability of those waves to reach the surface of the planet. So there is the cloud cover, and another thing is there's a layer of the atmosphere that is basically conductive. I think it's called the ionosphere. So you need to be able to pass through that to get to the surface of the planet, and then when you're going back, you still need to be able to pass through it again. But I think that is already being corrected for at the basic level. But the most thing is the cloud cover. So that really affects. When you're trying to measure something also like seagrass, you don't just need to pass through the atmosphere. You don't just need to pass through the cloud. When you get to the surface of the water, you still need to be able to pass through the water column to reach the seagrass that you want to measure. Another thing is when you're trying to measure bathymetry, but that is another thing entirely. So you need to be able to pass through the water column, and you need to be able to pass through at different levels at different places. So you need to be able to correct for that in the most accurate way. So that are atmospheric interactions that could affect the quality of the data. There's still several other things. I think I'm missing some, but for now, that is what I could think of off the top of my head that could affect the quality of the data.
All right. Much appreciated, sir.
Yeah, thank you for the response. But just in addendum to the question that was asked, based on the answer you just gave, you talked about you have to correct the data. Maybe you want to pass through different water column to get to seagrass or something. So how do you correct for that? Like,
So there are algorithms. These are
Okay.
being done by PhDs. There are algorithms that measure or that do the correction.
Okay.
I think the algorithms are based on what the reflectance, the rate of the reflectance that you're supposed to get when you're reflecting on different surfaces. It's the same principles that works for, take for example, seagrass. It also works for plastics.
Mm.
So different plastics reflect at different wavelengths or differently to different wavelengths. So what they reflect with is what you correct them for. So you go to the lab, you measure what the reflectance is, and then you put that into an equation, and then you apply it to the wavelength of whatever it is that you want to look at. So you know what the wavelength is, then you remove that wavelength from your satellite data, and then that gives you your actual measurement. Another thing is go to the lab, do the measurements, look at the reflectance in the lab, have a lot of data, and then train an AI model that would simply remove that reflectance in your satellite data. You could use several other algorithms, artificial intelligence algorithms for that. Maybe convoluted neural networks or artificial neural networks. I think we had a colleague that did his master's thesis on that.
Yep.
There are several means to be able to do that.
Oh, thank you for that. Because you just said that in the passing. I just want us to explore that. Yeah, thank you. Do we have any other person with any questions? Mr. Power, you want to say something?
Oh, no, 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 not at all.
Okay. So thank you once again. Thank you, Mr. Adekunle, soon to be Dr. Adekunle. Thank you for obliging us to come here, and we hope to see you again. Then thank you so much. Yeah, let's clap for him again. Let's give him a round of applause again. Thank you for your very busy schedule. Thank you for coming. We really appreciate. So yeah, to everyone, thank you for coming also, because without you here, there wouldn't be any lecture. So thank you for coming. And then next month we'll be meeting again, and the date for our seminar will be communicated to us in due course. So thank you once again for coming, everyone, and see you next month by God's grace. Bye.